Welcome to lesson 34 of my DP chemistry curriculum. Today we're going over structure 2.1.1. We're starting chemical bonding. So when metal atoms lose electrons, they form positive ions called cations. And when non-metal atoms gain electrons, they form negative ions called anions. That's the main point of what we're doing. We need to be able to predict the charge of an ion from the electron configuration of the atom. That's our main goal. And the formation of ions with different charges from a transition element should be included. So we're going to talk about the formation of ions with transition elements. Now, if you've been watching the HL videos, you already got a little bit of that, but otherwise, let's go. So formation of ions, why do we even need to talk about this? We know atoms make up everything, but they do that in a very specific way. Atoms make up everything through chemical bonds. So that means they have to bond to each other. But how do they do that? Well, what is a chemical bond? That's kind of one of the things you need to ask. What makes it different from any other bond? Are there any other bonds? Well, the main thing is that a chemical bond is just electrostatic interactions that hold atoms together. Which the big secret about chemistry is everything is just electrostatic interactions. It's all just positive nuclei and negative electrons interacting with each other, or even positive nuclei and positive nuclei interacting, or negative electrons and negative electrons interacting. You can kind of break everything we go through ever into these interactions, chemical reactions, bonding, uh, ionization, electron affinity. It's all the same idea. So you should just keep in mind, you're always looking for how these charges interact. So as we go through this, what we need to be able to do is that through electron configs, so we need to be able to do our electron configurations, but through these, we can recognize when an energy level is full. Now that doesn't seem super important. We remember energy levels as that period on the periodic table, or it's where certain sublevels like S, P, D, and F all reside. But we can see when they're full. We can see when inner ones are full or outer ones are full. But there's something particular about this. If the valence shell, meaning the outest energy level, so the valence shell energy level is full, and atom is stable. So they generally become stable when their outermost energy level is completely occupied with valence electrons. So atoms will do this to become stable. And we have two types of atoms generally that we look at. Metals, whoops, I was trying to write will. Metals will tend to lose electrons to create a full outer valence shell. A full outer valence shell. However, nonmetals, being the opposite, will tend to gain electrons to create a full outer valence shell. We've discussed this in a little bit of detail in earlier sections when we first talked about ions. So this is how we create ions. These become ions by losing or gaining electrons, because we remember that ions have a charge and they do that via the loss or gain of electrons. Specifically, we're going to reference two types of ions. We have cations. They are positive because they lose electrons. And we have anions, which are negative And that's because they gain electrons. If you lose a negative, you become positive. If you gain negatives, you become negative. A good way to remember cations and anions is you can think about a cat. If you think about a cat, and we're going to get a really bad drawing of a cat, cats have paws and therefore they're positive. So cations are positive. Anions are not cations, therefore they're negative. So you just have to remember the one. All right, so let's put this in a little bit of depth. Let's look at a metal or a cation, and let's look at it versus a non-metal. Oops, non-metal, an anion. And I'm going to use a real example. So we're going to actually pick sodium for our metal, and we're going to pick chlorine for our non-metal. And just to make my life easier, I'm going to do a little duplication trick. Just a little bit lower. There we go. So for my metal, let's pick sodium, which will become sodium plus, and we'll see why in just a moment, or I'll erase that for now. So sodium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. It's number 11. So what it's actually going to do is it's going to lose this electron, lose electron. And when it does that, the neat thing about it is it becomes stable because its new outer shell is the energy level below it, energy level 2. So this had a configuration of 1s2, whoops, 2s2, 2p6, 3s1. Its new configuration is 1s2, 2s2, 2p6. So its valence shell was n equals 3. Now its valence shell is n equals 2. And n equals 2 is a full shell. So it has now become stable. We put a couple square brackets and give the whole thing a positive charge. So this is an example of a metal cation. It gets smaller. We talked about this when we talked about ionic radius in trends. And we can see it physically getting smaller while also having a stable outer shell. Meanwhile, with our anion, chlorine has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 valence electrons. Or 17 electrons and 7 valence electrons. Very similarly, it's 1s2, 2s2, 2p6, 3s2, 3p5. It's going to gain an electron. So an electron's going to plop itself right there, and its new configuration will look a little like this. We still have the full inner shell, but now we also have a full outer shell. It's a bit more stable. It will gain that negative charge over the whole thing. Let's write chlorine in there with its new electron configuration being 1s2, 2s2, 2p6, 3s2, 3p6, and it is a full outer shell at n equals 3. So we went from missing an electron to having a full outer shell. Something you may notice or you may have already learned is that we have 8 valence electrons to create a full outer shell. Generally, that's what we refer to as the octet rule. The octet rule basically states that a stable atom slash ion will have 8 valence electrons. And that is generally what we refer to as a stable energy level. When the s and p orbitals are full, they create 8 electrons. So that's full s and p orbitals. Generally, though, this doesn't refer to transition metals. We're specifically talking about what we call main group elements. So this generally refers to our elements groups 1, 2, 13 through 18. So we're not talking about our transition elements. By the way, I will write that this is what we call main group elements. So if you ever hear the word main group elements, we're referring to 1, 2, 13 to 18. We're not talking about the transition elements. So let's just take a look at these groups. So I'm going to make us a little chart. Group 1, 2, 3, 4, 5, 6, 7, 8. And when we look at this chart, let's look at the valence electron config. So I'm not going to be doing energy levels, just the sublevels, the number of valence electrons, and the ion charge. So when we make our little chart, oops, almost there. We can fill this in. In group 1, all the valence configurations end with S1. 1s1, 2s1, 3s1, so forth. S2, this one becomes S2P1, S2P2, S2P3, S2P4, S2P5, and finally S2P6. So they're all trying to have the configuration of S2P6. That's a full valence shell. That's a perfect configuration. So the question is, how do they do that? Well, let's first look at our valence electrons, which is just the sum of electrons in the valence shell. In group 1, it's 1, 2, it's 2, 3, it's 3. Ooh, I've made a mistake. 13, 14, 15, 16, 17, and 18. So I don't specifically mean group 1, 2, 3, 4, 5, 6, 7, 8. I do mean group 1, 2, 13, 14, 15, 16, 17, 18. If you caught that, good catch. Anyways, 14, it's 4, 15, it's 5, 16, it's 6, 7, and 8. So the goal is to have 8 valence electrons, but we recognize that with metals, sometimes to get 8, we have to lose electrons because we reveal that inner shell, which has 8 anyways. So we can do that. So the ion charge is going to be, or you know what, even before we go to ion charge, let's say gain or loss. Gain, loss, electrons. 1 is going to lose 1. 2 is going to lose, oops, lose 2, lose 3. Now, 4 is an interesting case. It could lose 4 or gain 4. So what actually happens is nothing happens. These atoms in group 14 do not tend to become ions either way. 15 is going to gain 3. 16 is going to gain 2. 17 is going to gain 1. And 18 is also not going to do anything. It's already happy. So if we look at our last column and we talk about ion charge, losing 1 electron will create a 1 plus, which often we just write as plus. We don't usually include ones. Um, we don't need to include ones. It's kind of like putting a 1 in front of x, saying 1x when you could just say x in math terms. But 2 still becomes 2 plus, 3 becomes 3 plus. This does not have a charge. This becomes 3 minus, 2 minus, 1 minus, or just minus, and no charge. So we can figure out what the charge of atoms are going to be when they become ions just by looking at their position in the periodic table and recognizing their electron configuration, which tells us all of this. Something we need to go over before we move further and finish this section off is how do we talk about these? How do we represent them? So ions, oops, ions are represented by their element symbol with their charge as a superscript. So that's kind of like where you put squared when you're doing mathematical equations, like x squared or y squared, whatever. So for example, we can look at sodium, which becomes Na plus, not Na1 plus, magnesium, which becomes Mg2 plus, chloride, which becomes Cl minus, and nitride, which becomes N3 minus. So this is generally how we represent ions with element symbols. But we can also write and talk about them verbally. So if we're writing or talking about them, we write ions in two ways because it depends. If they are a cation, it's very simple. We just do name plus ion. So sodium becomes sodium ion. Magnesium becomes magnesium ion. There's no weird thing we have to do. We just say ion because sodium would talk about Na. Sodium ion specifically refers to Na plus. So we say ion to ensure that people who are reading know what we're talking about. However, if we have an anion, specifically an elemental anion, meaning like just one element, so chlorine or nitrogen, we have to do something a little different. Name, add the suffix "ide," and then you can say ion, but that's kind of optional. So for example, chlorine is no longer chlorine ion, it becomes chloride. And you can say ion or not. But if you say chloride, any scientist worth their salt knows you're talking about Cl minus. Nitrogen becomes nitride. Whoops. Nitride. And again, you can say ion or not. It doesn't actually matter. So when we write these, we have to be very, very careful. So lastly, the last part of this whole thing is what about transition elements? Because we've been skipping them. Transition elements. And those are groups 3 through 12 on the periodic table, that big middle section. So these are kind of problematic because electrons, I'll write it out, electrons are usually lost from D and S sublevels, as opposed to our alkali metals and alkaline earth metals, which just lose from our S. Therefore, we can have multiple cation charges for each transition metal. And they usually do have multiple charges. So you don't have to memorize all of them. And in fact, I believe it's in the data booklet as well. But there are a couple good ones that you should generally know right off the top of your head. So we'll go over the few common ions as well as how to write them out. Common transition ions. And this will be the last bit. So first off, we have chromium, Cr, which has the electron configuration Ar, and then it has 4s1, 3d5. You'll notice we fill the s and d orbital pretty simultaneously. It can form two different ions. It can be Cr2 plus, or it can be Cr3 plus, which, much like metals, we would want to say chromium ion, but how do we know which of these we're talking about when we say chromium ion? So with transition metals, we do have to learn a different way. We call this chromium 2, and that's Roman numeral, and we call this chromium 3 ion. So you can still add ion. Granted, the minute you put a Roman numeral, any scientist will understand you're talking about the ionic form of it. So we have to use Roman numerals to dictate which ion we're referring to. And then we can look at their new configuration. This is going to lose from both the S and the D, being 3D4. This one, again, it only can lose from the D now and becomes 3D3. So chromium is one of three common ions. followed by iron, one of our probably most common ions that we refer to throughout the DP curriculum. Ar, 4s2, 3d6. Its two main versions are Fe2 plus and Fe3 plus, which you can probably predict as iron 2 now, or iron 3. And as we look at these electron configurations, it's very similar to what we did with chromium. So we'll have 3d6 and Ar 3d5. All right, the last common ion is copper, which has our configuration Ar 4s1 3d10. Whoops. And it will become copper plus or copper 2 plus, becoming copper 1 and copper 2. And lastly, we'll write those configurations. Ar 3d10 and Ar 3d9. So that is everything you need to know about ions. A last little aside here with these. Sometimes when you're looking in a chemical storeroom, your bottle will not say copper 1 chloride or copper 2 chloride. It'll use actually the old names, which was cuprous or cupric, which is a little odd thing because copper would become cuprous or cupric. Whoops. I see. Cupric referring to the 1 plus and cuprous referring, or sorry, cupric referring to the 2 plus, cupris referring to the 1 plus. And iron, which has a symbol Fe, would become ferrous or ferric, taking from the old names of these elements, ferrous referring to the 2 plus and ferric referring to the 3 plus. So sometimes in a lab, you will not see copper 1 or copper 2 or iron 1 or iron 2 or whatever. You may not even see gold or silver. They'll have their old Latin names along with the suffix us or ic referring to the lower charge or the higher charge. So just something fun to look out for is different roots. So anyways, I hope this helps and have a great day.